respected session chair, Mr. Sinha, all other dignitaries of CPPRI, ICTA, and dear participants. My name is Malik, and I'm working as a senior project fellow at Cellulose and Paper Discipline Forest Product Division. So before starting my presentation, first of all, I would like to thank ICTA and CPPRI for giving me this opportunity to share our study in front of the experts of the pulp and paper industry. The topic of my study is integrated utilization of paper making raw materials through biorefinery approach. So my presentation is subdivided into the following sections. First of all, I will start with the introduction, in which I will give a brief background of the study, followed by the selected objectives of the study, then various materials and methodologies which have been adopted for performing the experiments, then results and discussion, conclusion, and at the last, acknowledgement. Now coming on to the introduction section. First of all, I will start with the raw material, which is the wheat straw. As we all know that wheat straw is a very established raw material in the pulp and paper industry. So wheat straw is an agricultural byproduct obtained after harvesting of wheat grains, and for utilization of wheat straw, it is generally either produced manually or by self-propelled baling machine. Now coming on to the composition of lignocellulosic biomass. Any lignocellulosic biomass including wheat straw is generally composed of three basic units, which is cellulose, hemicellulose, and lignin. Cellulose is a homopolymer of beta-D-glucopyranose units linked together by beta-1,4-glycosidic bonds. Hemicellulose is a mixture of polysaccharides which consists of pentoses, hexoses, and uranic acids. And lignin is a complex natural polymer which consists of predominantly building blocks of phenyl propane units, which are generally coniferyl alcohol, synapyl alcohol, and comaryl alcohol. Now, I'll tell you something about the chemical composition of the wheat straw and the fiber morphology of the wheat straw. Here we can see that the Claisen lignin content is minimum in the leaves, which is 14.18%. We can see that the hollow cellulose content is the maximum in the internode section. The ash content is maximum in leaf section, and it is comparable to internodes and nodes, which is 8.69 and 6.27%. Coming on to the fiber morphology of wheat straw, the average fiber length of the wheat straw is generally in the range of 1.03 to 1.60 millimeter. The average width of the wheat straw fiber is 9.3 to 15.7 micrometer. The approximate wall thickness of wheat straw fiber is 5.2 micrometer, and the approximate lumen diameter is 2.5 micrometer. This is a typical figure of a wheat plant. The uppermost part is called spike, which is subdivided into two sections, which is called O and glue. The rest is stem, leaves, and roots, as we all know. Now, the production and uses of wheat straw. The worldwide production of wheat straw is approximately 850 million tons. And if I talk about in the Indian context, India is the second largest wheat straw producing country globally, with an estimated production of 93.50 million tons. Now coming on to the conventional applications of wheat straw. Conventionally, wheat straw is being utilized as animal feed, as animal bedding, for mushroom cultivation, burning for power and generation, and for root thatching in villages. The other industrial application of wheat straw, as we all know, is in pulp and paper industry sector. And if we biologically convert the wheat straw, it can be converted into bioethanol, biogas, biodiesel, biobutanol, or microbial and other feed products. Now, if we see the quantities of agricultural waste, which is rice straw, wheat straw, corn straw, and bagasse, we can see that Asia is a potential market for the utilization of wheat straw. As we can see that in Asian continent, 140.20 million tons of wheat straw is available. And if I talk about the production share of wheat straw, here you can see that the maximum share is being shared by the Asia continent, which is 41%, followed by 37% in Europe, 18% in America, and 2% is shared equally between the Africa and Oceania continent. Now, as we all know that the Indian paper industry is typically divided into three sections based on the raw material. The first one is the forest waste, second one is the agro waste, and the third one is the waste paper waste, or we can also say recycled waste. Now, the R target of the study is basically the agro-based paper. Generally, we can see that the 11% production share is being shared by the agro-based paper mills. Now, coming on to the biorefinery platform, if I say the word biorefinery, what does that mean? A biorefinery is a facility or network of facilities that integrates conversion processes and equipment for the production of either power, biofuels and other value-added products from a single set of raw material. And if I say the word biorefinery in context of pulp and paper, these are the four major steps. First one is the pre-extraction of hemicelluloses. The second one is the pre-extraction of antioxidants. The third one is black liquor gasification. And the fourth one is the removal of lignin from black liquor. Now currently we'll be talking about the pre-extraction of hemicelluloses prior to pulping. Now this is the overall representation of a biorefinery concept in an existing pulp and paper mill. Here the bars which has been colored in green is being showing the steps of a biorefinery approach in an existing pulp mill. Now the need for research. Why this study has been undertaken at our lab? First one is the extensive availability of wheat straw globally, as I have already mentioned in my previous slides. The second one is the agricultural wastes are relatively free from wide price fluctuations as compared to wood, and there is a major advantage of using these as a feedstock for value-added products and justifies research and development efforts. The second and the major reason is that as we all know that during the pulping of wheat straw, most of the hemicelluloses has been dissolved in the black liquor along with lignin. And this black liquor is generally being burnt in chemical recovery boilers for the generation of power and for the recovery of inorganics, that is our cooking chemicals. However, the heating values of hemicelluloses, which is 13.6 megajoule per kg, is comparatively very low as compared to the heating values of lignin, which is 27 megajoule per kg. So I can say that it is very inefficient to burn hemicelluloses along with lignin in chemical recovery boiler. So what we can do is we can utilize these underutilized hemicelluloses. We can extract these hemicelluloses prior to pulping stage, and then these extracted hemicelluloses could be utilized for the generation of either biofuels, as we all know that pentose sugars can be converted in bioethanol through fermentation process, and it can also be utilized for the other value-added products such as for fuel and xylitol. The need to explore integrated pathways for exploiting biomass has gained more and more interest recently due to limited sources of energy, the increased concern of greenhouse gases and global warming, increased demand of energy in the world, and the need for alternative sources of renewable energy. Now, currently in the National Biofuel Policy of India, the center has moved forward for mixing of 20% ethanol in petrol by 2025 to 2026. So it is the need of the hour to identify the sectors from which the raw materials could be utilized and to identify the sectors from which we can retrieve those raw material for biofuels and other products. These are the objectives of the study. The first one is the recovery and estimation of reducing sugars from the wheat straw. The second objective was to evaluate the effect of pre-treatment on pulping quality. And third one was the comparison of physical strength properties of pre-treated and untreated pulp. Now coming on to the materials and methodology, the wheat straw was procured locally from Dehradun, and the proximate analysis of the wheat straw was conducted according to TAPI standard method. Under proximate chemical analysis, we have estimated ash, water solubility, alkali solubility, hollow cellulose, glycine lignin, alpha cellulose, and pentosane content. Now this is the overall representation of the study. Here we can see that the wheat straw has been pre-treated in three different ways. First one is the hot water, or we call it autohydrolysis. The second one is the mild acid. The third one is the alkali pre-treatment. The two fractions which was obtained after the pre-extraction, that is the solid residue and the liquid fraction. In solid residue was utilized for the production of pulp and paper, and the liquid residue, the TRS estimation was calculated. Now coming on to the reaction parameters of hot water pretreatment. For hot water pretreatment, The reaction was conducted at 100 degrees Celsius to 150 degrees Celsius for 60 to 120 minutes. For alkali pretreatment, wheat straw was subjected to 2%, 4% and 6% NaOH in the range of 100 degree to 150 degree Celsius temperature, and time within the range 60 minutes to 120 minutes. For acid pretreatment, the acid concentration was in the range of 0.001 normal to 0.2 normal. The reaction was conducted at 100 degrees Celsius, 125 and 150 degrees Celsius, again for 60, 90 and 120 minutes. Now coming on to the pulping of the wheat straw was conducted for both untreated straw and pretreated straw. The pulping was conducted at 3 different alkali charges, that is 12%, 14% and 16%. Handsheets were prepared from the pulp, and the evaluations of strand properties, physical strand properties, that is tear, tensile and burst index was estimated. Now these were the pulping conditions. The bath ratio was kept at 1:5. The alkali charge was varied from 12% to 16%. The maximum temperature was kept at 106 degrees Celsius, and the total time of the pulping was 180 minutes. The hand sheets of 60 GSMs were prepared according to TAPI standard protocols. The RA, TA, total solids were again calculated according to TAPI standard protocols. The total reducing sugars in the extracted liquor was estimated using dinitrosalicylic acid method using a UV visible spectrophotometer. The HPLC analysis was conducted for the analysis of sugars, and the field emission gas scanning electron microscopy was used to study the morphological changes between the untreated and pre-treated wheat straw samples. Now coming on to the results and discussion section. So this is the results of the proximate chemical analysis of pre-treated and untreated wheat straw. Here we can see that the water solubility of all the pre-treated straw samples has been decreased as compared to the untreated one. The minimum cold water solubility was found in case of hot water pre-treated, which is 2.07% as compared to the 11.38% of untreated one. If we talk about the hollow cellulose content, the hollow cellulose content was more or less similar to the untreated wheat straw. The alpha cellulose content was somewhat increased as compared to the untreated one, and the pentose content was decreased drastically in case of acid pretreatment, because which I will be talking about in the next slides. So these are the results of the TRS estimation in the hot water pretreatment. Here we can see that the minimum TRS was extracted at 100 degrees Celsius for 60 minutes, and a significant increase in TRS extraction was observed when the temperature was raised from 125 to 150 degrees Celsius. A maximum TRS of 15.01% was extracted at 150 degrees Celsius for 120 minutes. Now these are the results of the TRS estimation in alkali pre-treated wheat straw liquor. Here we can see that a gradual increase in TRS was observed when the time of the reaction was increased from 60 to 120 minutes at both 100 degree and 125 degrees Celsius. From the figure, it can be observed that initially only 2.58% TRS was extracted at 2% NaOH, 100 degrees Celsius for 60 minutes, which was increased up to 8.65% at 6% NaOH. Temperature 125 degrees Celsius for 120 minutes. Now this is the result of the alkali pretreatment, TRS extracted at 150 degrees Celsius. A substantial increase in TRS was observed when the time was increased from 90 minutes to 120 minutes at 150 degrees Celsius. A maximum TRS, that is 13.20%, was achieved when the wheat straw was pre-treated at 6% NaOH, 150 degrees Celsius for 120 minutes. Now coming on to the results of the acid pretreatment, the TRS extracted at 100 degrees Celsius shows a considerable increase in TRS when the acid concentration was increased from 0.05 normal to 0.2 normal. And the minimum TRS, that is 1.39%, was extracted at 0.001 normal acid concentration for 60 minutes at 100 degrees Celsius. Of all the pretreatments, acid pretreatment extracted maximum TRS, that is 38.78% when pretreated with 0.2 normal H2SO4 at 150 degrees Celsius for 120 minutes. And I must mention that, however, the purpose of our study was the controlled extraction of sugar, because hemicelluloses also play an important part in the in the strength properties of the paper. So the target of the TRS extraction was only to achieve extract those 60 to 70% of hemicelluloses which have been washed in the black liquor. These are some of the images taken during the study. This is the HPLC chromatograph of the hot water pre-treated wheat straw liquor. Here it can be seen that the maximum concentration is of xylose sugars, which represent hemicelluloses, that is 63.06%. Glucose was 3.05% and arabinose was 25.18%. This is the HPLC analysis. Excuse me. This is the HPLC chromatogram of alkali pre-treated straw liquor. Here again the maximum concentration was of xylose, that was 64.10%. The glucose concentration was 7.76% and the arabinose concentration was 15.64%. This is the HPLC analysis of acid pre-treated straw liquor. Here you can see that the concentration of glucose has been increased. This can be attributed to the fact that during acid hydrolysis some of the amorphous cellulose have been hydrolyzed into the liquor. These are the field emission gun scanning electron microscopy images of untreated wheat straw. Here we can see that the surface is very much smooth and compact. These are the images of hot water pre-treated wheat straw, which was conducted at 150 degrees Celsius for 120 minutes. These are the images of alkali pre-treated wheat straw. Here we can see somewhat that the surface of the fiber has been distorted somewhat. And these are the FSM images of acid treated. Excuse me. Now these are the FSM images of the acid pre-treated sample. Here we can see that the surface of the fiber has distorted most as compared to the hot water and alkali treated. This can be attributed that the pre-treatment of wheat straw could distort the cellulose, hemicellulose and lignin network during pre-treatment. Now these are the results of the pulping study. Figure A shows the total pulp yield at 12% alkali charge. Figure B shows total pulp yield at 14% alkali charge, and figure C shows total pulp yield at 16% alkali charge. Here we can see that the total pulp yield decreased on increasing the alkali charge from 12% to 16%. Maximum pulp yield 55.97 was observed for acid pre-treated sample at 12% alkali charge, and the minimum pulp yield was observed for hot treated wheat straw sample at 16% alkali charge. These are the results of the screening, that is the pulp rejects. The pulp rejects also decreased on increasing the alkali charge from 12% to 16%. The maximum pulp rejects, that is 2.24%, was observed for acid pre-treated wheat straw sample. Minimum pulp rejects, that is 0.11%, which is very much similar to the negligible, was observed for alkali pre-treated straw sample. The pulp rejects decreased after alkali and hot water pre-treatment as compared to the untreated wheat straw sample. Now these are the results of the screen pulp yield. The screen pulp yield also decreased on increasing the alkali charge. The highest screen pulp yield 53.78% was observed acid pre-treated sample, and 2.31% increase in screen pulp yield was observed at 14% alkali charge as compared to the untreated wheat straw at 16% alkali charge. Now these are the results of the kappa number. The kappa number was decreased on increasing the alkali charge from 12 to 16%. The kappa number of the acid pre-treated wheat straw pulp increased as compared to the untreated wheat straw pulp. Hot water and alkali pre-treated wheat straw pulp achieved lower kappa number than the untreated wheat straw pulp. Lowest kappa number, that is 14.9, was observed for alkali pre-treated wheat straw at 16% alkali charge. Now these are the results of the CSF. The CSF was decreased on increasing the alkali charge from 12 to 16%. Minimum CSF was achieved at 16% alkali charge for untreated wheat straw sample. The CSF increased slightly for all the pre-treated wheat samples as compared to the untreated wheat straw pulp. Now these are the results of the black liquor analysis. The total solids and RAA was calculated in the liquor. Here you can see that the total solid content was decreased as in case of all the pre-treated sample as compared to the untreated one. The RAA was decreased slightly as compared to the untreated one. Now coming on to the results of the physical strength properties. Here the tear index of pre-treated and untreated wheat straw pulp at different alkali charges. Figure A shows the tear index without blending of long fiber. Here we can see that that at 16% alkali charge, the tear index has been increased slightly as compared to the untreated one for all the samples. After blending of 10% of long fibers, we can see that if we talk about 16% alkali charge, we can see that the tear index has been increased slightly from 6.94% to 8.01% in case of untreated one, and from 7.08% to 8.54 sorry not percent 7.08 to 8.54 for hot water pre-treated sample. Now these are the results of the tensile index. Now after pre-extraction, the tensile index of the prepared handsheets were decreased as compared to the untreated one. So this can be attributed due to the loss of hemicellulose, as most of the hemicellulose was extracted during the pre-pulping stages, and these hemicelluloses play a significant role. So this loss in tensile index may be attributed to the loss of hemicellulose during pre-extraction stage. However, after blending of 10% of long fibers, this loss can be compensated. Now this is the results of the burst index of pre-treated and untreated wheat straw pulp, again at different alkali charges. Here also we can see that the burst index has been decreased for all the pre-treated straw sample as compared to the untreated one. Again, the reason is same, the loss of hemicellulose during the pre-extraction stage. Now coming on to the conclusion, the hot water alkali and hot water alkali and acid pre-treatment extracted 15.01%, 13.2% and 15.62% reducing sugar respectively. Acid pretreatment performs better in terms of reducing sugar's recovery as compared to the hot water and alkali pretreatment. The HPLC analysis confirmed the presence of xylose, arabinose and glucose monomers in the pre-extracted liquors. The FE-SAM analysis confirmed that the pretreatment could distort cellulose and hemicellulose lignin network. The total pulp heat decreases for all pre-treated and untreated samples when the alkali charge was increased from 12 to 16%. The pulp rejects were also decreased for all the pre-treated and untreated wheat straw samples on increasing the alkali charge from 12% to 16%. An increase of 2.31% in screen yield was observed at 14% alkali charge in case of alkali pre-treated wheat straw as compared to the untreated wheat straw at 16%. The kappa number decreased significantly for alkali and hot water pre-treated straw sample by 13.87% and 12.3% respectively, while an increase in kappa number by 11.3% was observed for acid pre-treated straw sample. The tear index of handsheets, as I have mentioned, was increased slightly after pre-treatment. The tensile index of handsheet decreased after pre-treatment. The burst index of handsheets was also decreased, and tear, tensile and burst index of all the pre-treated and untreated wheat straw pulp samples improved after blending 10% long fibers. The tensile and burst index of hot water and alkali pre-treated straw sample was similar to that of untreated straw sample after blending 10% long fiber. Addition of long fibers to the pre-treated wheat straw pulp may compensate the declining strength properties of paper, mainly tensile and burst. The hot water and alkali pre-treatment was found conducive for paper production as compared to the acid pre-treatment. Now, from the study, these were some of the future prospects. Techno-economic analysis must be conducted for all the incorporation of an additional pre-treatment step in a pulp and paper mill. Further studies on utilization of extracted hemicellulose for the generation of bioethanol or other value-added chemicals can be undertaken. It is suggested that a study on the variation of time and temperature during pulping can also be conducted to assess the change in the pulping and strength properties after pre-treatment. Possibilities can be explored for scaling up the outcomes of the study, and the detailed mass balance needs to be calculated. Conditions for the production of dissolving grade pulp as well as efficient utilization of black liquor for the production of various value-added products can be explored. In the end, I would like to acknowledge Director FRA, Dehradun, Director Sess, Punjab University for providing the facility of SAM, Director IIT Dehradun for providing the facility of HPLC, Dr. Vikas Rana, Scientist at Cellulose and Paper Discipline from FRI, Dr. P.K. Gupta, Dr. Gyanesh Joshi, and my fellow researchers at FRI. Thank you.